Okay, good afternoon, everyone. So today, for this week, we're going to be looking at bivariate tables, which will set us up for the chi-squared testing next week. I think this chapter will be pretty straightforward. To be honest with you, if it were me, I would maybe put this chapter earlier. Though I see how it goes well with the chi-squared testing because, well, as you'll see, basically the creation of these tables in order to test for significance, we use the chi-square test for next time. So I see how it couples well with the next chapter, but this is kind of going back a little bit to like organization and like the graphic organization of the data, figures. You think back to like the histograms and pie charts, it kind of goes along with that a little bit, but either way, I think this will be a nice little break. No funky equations this time, as was the case in the hypothesis testing. I know the equations can get tough there. This is a little bit more straightforward, so it'll be maybe a little break for you. And then obviously I'll upload the second round of slides with the video for this, and you'll have that to complete the assignment on bivariate tables. So let's go ahead and get started. Shouldn't take too long today. Just to begin with a little bit of some definition, some vocab. When we talk about cross-tabulation, cross-tabs is, I guess the shortened term for it if you want to abbreviate, but cross-tabulation is this technique where you can analyze the relationship between two nominal or ordinal variables. So keep in mind, we're always looking back to what type of variable it is, and it always matters. It never goes away. So for cross-tabulation, we look at nominal or ordinal variables. And they've been organized into a table basically where we're looking at the relationship between two variables. So cross-tabulations are one particular type of bivariate analysis. And if you break down this word bivariate, two variables, pretty simple. It's this method to detect and describe the relationship between two variables, particularly nominal and ordinal variables. So, think of it in a way of, we want to look at an independent and a dependent variable and their relationship. Okay. So a bivariate table is simply it's a graphical table that displays the distribution of one variable across the categories of another. Again, it's always nominal or ordinal, and it's a table that shows this bivariate analysis. So think of it as the combination of two frequency tables. So I could look at the frequency of let's say first, second, third, and fourth year students at Valdosta State as an ordinal variable, and I could look at that in terms of whether or not you graduated, or graduation wouldn't make sense for first year. Let's say whether or not you're in an extracurricular activity or not, yes or no. So that would be the nominal variable there. So basically you have a variable 1 in the column and variable 2 in the rows. And you've seen this kind of stuff before. Let me flip over to the book real quick. Stuff like this, where you have one variable of home ownership and another variable of race, and then the breakdown there. So again, I kind of sounded like a broken record, but make sure you're reading your book. Obviously, it's invaluable at this point. This is chapter 10. Okay. So bivariate tables always have these features. These are the 6 kind of big ones. Although 1 and 6 shouldn't be new to you. The 2 through 5 is kind of the new stuff. So number 1, always a title. So when you do your homework, make sure you title your tables. Just something simple like a bivariate table of, and then your 2 variables. But just some way to identify what your variables are that you're analyzing, and that that you're looking at the relationship between 2 particular variables. So you always want to have a title, and all your book examples will have titles. Okay, and then number 6, I got just to jump ahead to what always a source. I always want to know the source of the data. So typically at the bottom of the table, and hopefully you're kind of used to that at this point. It's 2 through 5 that's the new stuff. So bivariate tables always have frequencies or percentages for 2 variables. This is this is important. I would say this is maybe the most important thing, that we always want to put our independent variable in the column variable. So the attributes across the top. And then the dependent variable will be the row variable. So the attributes are down the side. I'm going to work out an example here in a second, but it'd be worth committing to your memory that row, dependent variable, column, independent variable. So I don't know if you can think of a nice way to memorize that, go for it, but we always want to put the dependent variable in the rows and the independent variable in the columns. Mostly because we read right to left in the United States, and it just helps with readability when you have it like that. There's no, I guess, there's no mathematical reason. It's more just convention and ease. And I think you'll see in a sec that it just helps make the table more readable. Because at the end of the day, that's all you're doing, is you're trying to convey data quickly and concisely and clearly to an audience. Okay. So if we put the independent variable in the columns and the dependent variable in the rows, across the top and the sides are going to be your attributes, but the intersection of a row and a column is called a cell. And that should hopefully be something you're familiar with. Cells are sort of the intersection of the row and the columns in terms of like the matrix that you're looking at. I'm gonna show you something from the book here in a second as soon as I get through this. So the column and the row totals are the frequency distribution for each variable respectively. Row and column totals are called the marginals. So the total number of cases is reported in the intersection of the marginals. So basically what you have in the cells are kind of the intersection between the two, and then the marginals relate specifically to one variable or the other. And then lastly, the table is described by row times column. So again, it's your dependent variable by independent variable. The column variable is your independent. So a 2x2 table, the dependent variable would have 2 attributes, the independent variable would also have 2. But in a 3x2 table, the dependent variable would have 3 and the independent variable would have 2 attributes. I mean, obviously these tables can get huge. I'm not going to overwhelm you with making a 10x10 table, but expect something like a 4x2 or 4x3. That's conceivable. Okay, so let's take a look in the book. This is table 10.2. So if you look, here's the raw data here. Actually, I guess it starts on the first page. So basically you're collecting, let's say, what do we have? 17 respondents, and we're asking them their race, I guess it's just bivariate black or white, and then whether they own or rent their own home. So if you think about it, I mean, just looking at that, which is going to be the independent variable, which is the dependent? Does it make any sense for your home ownership status to predict your race? No, that kind of seems silly. It's backwards. It's that the race you identify as, that could impact or predict your home ownership likelihood. So our independent variable is going to be race. Our dependent variable is going to be home ownership. We use race to predict home ownership in this case. Okay, so here's the breakdown of whether a respondent, their race, and their home ownership, and then it's collected in this little table. So basically, you have you have your race, your race across the top, so your column variables, and then your row variables are your dependent variable, which is the home ownership stuff. So dependent variable in the rows, independent variable in the columns. And you can see the cells, which are the intersections. So this would be, I guess this would be white, own home, white, rent, black, own home, black, rent. I suppose they didn't mark which one is which, but either way, I mean, you could calculate this on your own, I guess, but just for the sake of, let's just put white and black here, just like that, just to help us out. So these column variables, I'm sorry, the column variable, this is what I'm talking about here, is the independent variable, and it's written across the top. See how these columns correspond to black and white? These are your 2 attributes for race. And then your row variable is your dependent variable, Again, your two attributes across the rows. This is owner, rent, home. And the general, generally what you're looking at is an independent variable predicting a dependent, right? And your independent variable is race, predicting home ownership. Okay? So I think the cells are pretty clear. What tends to, I don't want to say confuse people, but what can be a little tricky is the marginals, but the marginals are just the row totals. So let's take a look at this. It's 9 and 8. This just tells us that 9 people in the sample own and 8 people rent. And then the column marginals will tell us that there's 7 white people in our sample and 10 black people. Okay? And obviously the column marginals and the row marginals should add up to the same. They're both 17. But the actual numbers will be different, but they'll still add up to 17. So see how this just tells us that there are 10 people who are black. And then of the people who are black, 3 people rent, 7 people own. That's all it is. And then your total. I should have put on here too that it's always nice to put the total number of cases on there. Excuse me. And this is outlined in your book too. So the whole kind of 6 things you always include. Let's see. Okay. So I think we should be good on that. Key things to know: independent variable, columns; dependent variable, rows. What's a cell? What's a marginal? Okay. So let's do a little example. I've got this little bit here. So basically asking people, and this is not from your book, asking people whether or not they have health insurance, and then whether or not they visited a doctor this year. Okay? So as you can see, I mean, I've already set this up. I could just give you the raw data, but I could, and have you, put the frequencies in the table. Just for ease, I already created that. So a couple things to keep in mind. Remember, the independent variable, the predictor variable, is in the columns. So here's your column variables: health insurance status, insured, uninsured. And then visiting a doctor is your dependent variable. These are going to be the row variables: visited, did not. So if you look, this is a 2x2 table. Why? Because there's 2 attributes for the dependent variable, 2 attributes for the independent. And if you think about it too, I mean, it makes sense. Your health insurance status would potentially predict your likelihood of going to the doctor. That's independent, dependent. The flip of it would be that the doctor, whether or not you visited a doctor, determines whether you have a health insurance. That's backwards. So a lot of times it's helpful to just draw this stuff out. Independent variable, health insurance status; dependent variable, visiting the doctor. And then you'll set up as such. Okay, so if you look, these are the cells, right? These are your marginals. So your cells tell us that 20 of the 33 people who were insured visited a doctor. 13 of the people who were not insured did not visit a doctor in the last year. So 33 people are insured, 17 people are uninsured, 28 people visited a doctor, 22 people did not. Again, these both add up to 50. Why? Because, I mean, it's the same data. So keep in mind too that we're just looking at the frequencies of 2 variables, right? We could look at just the frequency of insured, uninsured. That's 33 to 17. We could look at the frequency of visited a doctor versus not visited, 28 to 22. We've done that before. This is basically combining the frequencies of 2 variables and looking at the relationship between them, specifically focused on. So it's like the marginals are stuff you've done before. It's the cells that are different, because these 20 people are people who are insured and visited a doctor. These 13 were insured and did not visit a doctor. So again, of these 50 people in here, we break them down between these 4 cells, right? So there's 50 people total in the sample. And here's how they're broken down between insured and doctor visits. Again, I think this should be pretty straightforward, but if you have any questions, obviously let me know. But let's work out this example, because what I will often give you is a table with just with raw frequencies, so the count. But really to compare, Well, let's think about this. Why can't we compare? Because I mean, I can look at this right now and say, wow, there's, of the people who were insured, there's, 20 here that visited a doctor versus 8 people who were uninsured that didn't visit. I'm sorry, 8 uninsured people that visited a doctor. The problem is that these are different, they have different denominators, right? We have more people that are insured than uninsured in our samples. So it stands to reason that obviously more people who are insured are going to visit a doctor because there's more of them. I mean, there's almost twice as many in our sample. In order to compare the two, in order to compare insured versus uninsured people in terms of doctor visits, we want to put those into percentages. Because then we're not limited by differences in the sample size. Again, you can see there's only 17 people who are uninsured. So at most, the number of people who are uninsured the most people that could have visited a doctor would be 17, which would still be less than the number of insured that visited a doctor. But the only reason is because there's just more of those, there's more insured people. Same here, there's more people who visited a doctor than did not. So we want to look at the percentages in order to compare them. So that's going to be your first step in the homework, is to convert these frequencies into percentages. Okay, kind of like what I just said here. So to assess the relationship between the variables, we need to convert the frequencies into percentages because the row and column totals are not equal. So the 2 steps in order to do this, we want to calculate percentages within each category of the independent variable and then interpret them. So what does that mean? I want to, so if we think that the independent variable is our column variable, and we want to calculate percentages within each category of the independent variable, we want to calculate percentages down. Let me say that again. We want the percentages within each category of the independent variable. So in order to do that, we need to create percentages, but we need to sum them down, the columns. Okay? So basically what we'll want to know is, of the insured people, how many visited a doctor? Of the uninsured people, how many visited a doctor? Rather than vice versa. Okay? So I set this up here. So here's what you have. I set this up on the page. So visited a doctor this year, yes, no, your total. These are going to be your marginals. And then insured, uninsured, total. These will be your marginals, and this will just be your total N. Right? We know what this is. It's 50 already. Okay. But what we really want are the percentages. That way we can kind of compare within the independent variables and not be kind of limited by the differences in the sample size. Okay? So what I'm going to do here, so I've got 20, so I have 33 people who are insured. So I have 33 people who are insured. And of those people who are insured, 20 of them visited a doctor. And of those people who were, out of 33, sorry, that's a bad typo. Okay, so 20 out of 33, 20 of the 33 insured people visited a doctor. So that means 13 of the 33 people who were insured did not visit a doctor. And these numbers, they're just coming from here. So 20 people who were insured visited a doctor out of 33. 13 out of 33 who were insured did not visit a doctor. Gosh, tongue-tied. Okay? So it's relatively simple. You just divide 20 by 33, and then you divide 13 by 33, and you get about 60%, close to about 40% there. You're going to do the same thing here. So of the uninsured people, how many people visited a doctor? Well, that's 8 of the 17, right? So we have 17 uninsured folks, 8 of them visited, 9 didn't. So we set that up the same. And do kind of the same thing, and you get about 47% and about 53%. Okay. Now the total this is just going to tell you the percent that visited a doctor, right? Because this is going to be your marginal. So this is basically just the percent that visited, the percent that did not visit. This is going to be 28 over 50. This is going to be 22 over 50. So if you can't tell, your numerator is always going to come from your cell. Your denominator is going to come from the marginal. Numerator, denominator, numerator, denominator. And then for the marginals themselves, we're going to take the marginal and divide it by the total number, right? So, and this is, all this tells us is the frequency of one variable. 28 out of 50 people visited a doctor. 22 did not. So then we convert those into percentages and we get about 56 and 44. We can do the same thing with the bottom. Bottom is going to be easy. And this is sort of the trick, is that your columns should always sum to 100. So basically, what we're doing here with the total, right? So 60, 40, well, that's 100%. And then this is going to be 100% as well. So see how your columns always sum to 100, and the column variable are the independent variables. So it's kind of like, I mean, we read left to right, so we could quickly see, okay, so of those who are insured, 60% are going to the doctor, 40% are not. And then of those who are uninsured, it's closer to 50-50. It's 47-53. And again, I just rounded here, but these numbers that I have here, it's the same thing. I just wanted to, show you where they were coming from. So a little bit more of an even breakdown, and then the row marginals tell us that all this says is that 56% of the people in our sample, so 56 out of the 50 visited a doctor, 44% did not. Your columns will always sum to 100 if you put your independent variables in the column, and you should. So independent variable, insurance status, predicting doctor visits, your columns will always add up to 100. And you could put the n there if you'd like, I think it would be wise to include that unless you already have it. So if I give you the data and it has the frequencies, don't feel the need to put it in again. But if I don't, obviously it's it's useful. The one thing that you always definitely want to have in there is the 50, because if I'm seeing 60%, 40%, 53, 47, I'm like 53 of what? Well, I need to know what I'm looking at. So you should include the totals. And all this tells us is that 33 people here are insured, 17 people are uninsured. If you wanted to figure out what those were, well, it's going to be about, this is going to be about 66, 34%. 2/3, 1/3, thereabouts. So that's really it, at least for today. There's another layer I want to add on Thursday, but it's not too complicated. I think this should go down a little, this should be a little, I don't want to say easy, but I think this will be a little bit more straightforward for you. So I'll upload your assignment for you, just where you're doing a bivariate analysis. But I should also say there's no general rule to focus on the differences, but any difference of about 10%, you should maybe kind of be, that seems like a significant difference. But like I said, next week, we'll look at the chi-squared test to see if the differences found in the bivariate tables are different. Obviously, larger differences indicate greater variation, smaller difference indicate less variation. So let's just take a look back here and wrap up. So if you're comparing visiting a doctor versus not visiting a doctor, insured people are visiting the doctor at about 60% versus 47% uninsured. So it's a 13% difference. That does kind of beat our 10% general rule. So it would be something to keep an eye on. Are those significantly different? We couldn't really say. This is where we do a chi-squared test, and I'll show you how to do that next week. But in general, I mean, the general conclusion here is that insured people are going to the doctor more than uninsured people, which I don't really think is going to be a big surprise to anybody. But this shows us statistically how that's happening. of the people who are uninsured, slightly more are not visiting the doctor than are, but although it's close to about a 50-50 breakdown, whereas of the insured people, it's closer to a 60-40 breakdown. So the question is it significantly different? You could kind of, I mean, you could assume that it probably is, but the chi-squared test will tell you definitively if there is. So in the homework, I'm going to ask you for like your conclusions. A couple conclusions you could draw from this would be insured people are more likely to visit a doctor compared to uninsured people. And then the reasons why, obviously, are numerous. Costs, out-of-pocket costs. You let your mind wander with that, but bring in some things about sociology that we know. Who are these people who don't have health insurance? Well, they oftentimes are people whose jobs don't provide them, or people working in like temporary positions, part-time kinds of stuff. Typically, this is people without health insurance compared to people with health insurance tend to be a little bit lower income, so that could relate to it. So, I mean, if I'm seeing this, I'm concerned because people who maybe are lower SES and don't have insurance are visiting the doctor less. So in terms of a health vulnerability standpoint, they're going to be more vulnerable to things like COVID right now, or obviously like other health issues because they're not going to the doctor regularly. So this would provide evidence that insurance does help people go to the doctor on a regular basis and hopefully catch issues early enough so that they don't become problematic. There's a lot to say about preventative health care and how much money that saves in the long term, and honestly how much better it is for people and improving their lives and keeping them from becoming sick and then trying to cure them once they're sick, rather than that obviously trying to prevent that stuff from happening before it gets too dire. So that would be like your conclusion from this. Nothing super groundbreaking, but plenty to talk about. And that would be your conclusion. So let that ruminate a little bit. I would say big things from today you want to know: column, independent variable; row, dependent variable; and then what a marginal and a cell is. And if you have any good ways to remember the column being the independent variable, let me know. This is kind of silly, but the way I do it is when I think of a column, I think of like Roman or Greek, and independent variable, it sort of looks like the number, when you draw independent variable, it looks like the number 4, Roman numeral 4. So I think Roman column, I don't know, that's the way I remember it, but if you have anything better, let me know. But obviously it's not something you have to totally memorize, but it's you do want to know this, because when you're setting this stuff up, you always want to when you think you're what's my independent variable? Well, I'm using, if my IV predicts my DV, well, I'm really using health insurance to predict doctor visits. So if my health insurance is independent, I want my independent variable in the column, so I want these variables going down. So insured, uninsured, visited, not visited. So I'll put the homework assignment up, see what you can do. There's a couple examples from the book. I'm going to keep it pretty straightforward, pretty similar to what you've seen. I don't want to throw any surprises at you. So let me know if you have any questions. Good luck, and we're kind of hopefully moving through. Hopefully everybody's on board and doing okay with keeping up with stuff. But if you have any issues or any questions, please let me know. Again, I'm going to be flexible with the due dates. Get it in as soon as you can. But I'm kind of looking for completion over timeliness. So just make sure you're getting your stuff done. Anyway, right under 30 minutes. So I will hit you with another video on Thursday and go from there. So good luck. Thanks. Bye.